Cool. Well, thanks everybody for joining us, especially if you just heard about this last minute. But uh, we are going to continue to do these Reach workshops as long as people start showing up. So thank you for joining us. And what we're going to learn, or what these guys are going to walk you through, the Reach founders, co-founders, Chris and Jay. Thank you guys for taking the time, as always. And you're going to learn how to build smart contracts in a smarter way and build blockchain DApps using Reach. So with that, I'm handing it over to you, Chris. Let's take it.
Thank you so much. I appreciate it. So, like Gabe said, my name is Chris Winter, and this is Jay McCarthy. We are the co-founders of Reach. I am the CEO, and Jay is the CTO. So what we're going to do today is I'm going to kind of explain the background behind Reach, why we started, kind of a real high overview of what we are, and then I'll pass it over to Jay to do a good deep dive into the coding, and then probably most likely dig into more advanced features after the walkthrough has been done. So what Reach is and where we started. So about 2 or 3 years ago, we really kind of looked at the space and asked the question, where are all the developers? There's at the time, I think only around 1,000 developers working on blockchain full time in the entire world, when there's 20 to 30 million developers in the world. Why is there such a big difference between the two? Now, so we started researching, started asking, started talking to developers, and the big reasons that keep popping up is all around how difficult it is to build blockchain applications. And not difficult in just one single way, but difficult in multiple different reasons. Now, one of the reasons is that programming in blockchain in the current with the current tools is a very low level of development. It's programming at the level of a state machine. You have to actually program the manipulation of state yourself, and it just requires a lot of manual work to build anything. So it's just like a different type of thinking. It's not nearly like similar to your traditional centralized development today. The next thing is that because of how low level it is and how much work that has to be done, developers were running out of steam. They were starting, getting frustrated, and quitting before they ever even developed any type of application. And the next really issue that came up is that it was too low. So it was too low level, and it was take too long to do. And so it was a much higher chance of actually writing a bug. But the thing with blockchain is if you write a bug, it's usually game over. It's in game because of the immutable state of blockchain. So it was very risky to actually write an application. And then finally, the state of blockchain development today is very similar to the state of development on the personal computer in the late 70s and the early 80s, where you kind of had to actually write an application that was specific for a piece of hardware. And if you wanted to launch on a different piece of hardware, you would have to rewrite that application. And that's where blockchain is today, is when you want to write an application, you have to write it specifically for Ethereum or Cardano or Algorand or any of the different protocols. So the developers are asking themselves, well, what if I spend 6 months to a year to become good enough to write a real application in blockchain, and that chain goes away, or there becomes another chain that becomes more popular? Did I just waste a whole year of my life? So we kind of balled all of that up and said, okay, we need to fix these issues. And what we kind of had to answer the question is, like, do we follow the traditional product path where we iterate on one of them and kind of make it a little bit better and work with customers, or do we forget how it's currently done today and ask the question, how do we make it 10 times or even 100 times better than what it is? And we decided to go with the latter, even though it was a much bigger risk. And that's where where Jay comes in. He'll kind of give an intro to who he is, but he's a computer science researcher, got his PhD from Brown, and has been studying programming languages, compilers, formal verification, many different things. So he was the perfect person to go all in by building a a very elegant solution that really nobody else has kind of thought about doing it this way, especially for blockchain. So this is where Reach came. Reach addresses all three of the major issues, and it addresses them in a way that it makes it exponentially better. Number one, Reach provides a programming language that is a subset of JavaScript, so it's very familiar to most developers, that allows for developers to write at the level of the participant rather than the level of the state machine. And because it's a much higher level of abstraction, it's much easier to understand and much faster to write. So to give you an example of like a real use case, there's an application out there called AlgoNim that I interviewed the developer, and it took him 6 weeks, or spending 3 to 4 hours a day to write this pretty simple decentralized application. And after talking to him, I thought like this would be a great use case to rewrite in Reach. So I asked Jay to write it without him having any previous information. And by the time I sent him the GitHub, there was 1 hour that passed before he wrote me back and said, okay, I wrote it. So he was able to rewrite a application that took 6 weeks for a traditional developer writing in the blockchain way. It only took him 1 hour. So it's much, much faster to write in this way because it's a higher level. Now, the second thing that we really kind of focus on is the compiler. The Reach compiler takes that high-level Reach language, and it's formally verifies the output to actually give extra guarantees of correctness. And kind of give you an idea what formal verification is, it's been around for a very long time. It's used by NASA or hardware manufacturers, but what it is it's the art of taking your application, turning it into a math problem, and then proving it to be correct in all potential realities. Now, this is very similar if you remember back in geometry when you were given a formula and you wrote out by hand to prove that the formula is correct. It's very similar, except that this is to your entire application. Traditionally, though, to get your application formally verified, you would have to go to a third-party auditor or a consultant, and they would have a team of genius mathematics PhDs, and they would create a long spec, and they would create simulations and prove out that your application is correct. But Reach automatically generates these proofs through the compilation process, and all you have to do is put inline assertions to tell the compiler what your application is supposed to do. So it puts the power of formal verification in the hands of just a traditional developer. And then finally, what we did is we've abstracted the protocols themselves away from the development or the blockchains. So you have the ability to write your application and launch it on any chain. So being able to launch on any chain is really cool, but the real cool aspect of this is that what we're doing is we're making the Ethereum developer, the Algorand developer, the Cardano developer obsolete. And what we're doing is we're creating blockchain developers. And now Reach has the network effect of all blockchain developers being able to help each other without having to worry about what protocol they're actually writing on. So that's kind of like a very, very high level example of what Reach does. Jay is going to walk you through on the more specifics on how it happens. But Jay, you want to take it over from here?
Howdy. Yeah, so I will talk just very shortly about myself and my background, as Chris mentioned. So I am a associate professor at the University of Massachusetts. I've been researching formal verification, programming language design, distributed systems, and cryptographic protocol verification, for the last 15-ish years. Basically what I've found is that every time I'm presented with a new problem related to blockchain stuff that Chris tells me about or whatever, Chris is extremely hip in the blockchain world. I'm like a total old fart. I don't really know anything about what people think are cool these days. But anyways, I'm like, oh yeah, that reminds me of this paper that I wrote 10 years ago, or this other paper. And so what I've been able to find is that a lot of the sort of medium range ideas that are in those fields of verification, programming language design, etc., have a natural place to come together in the blockchain world. What I'm going to do is I'm going to share my screen right now, and we'll share that. And then I'm going to turn off my video because it makes it so that my video decoder or encoder turns off. And so if you have, something that you want to add, just, interrupt. And you can also type in the chat if you don't want to, talk. So what you see right here, just to point out, so there's our documentation, which is at docs.reach.sh, and the front page is loaded right here. Then over here, I have a terminal window showing an example program. And, we support VS Code and things like that, in Atom. But as I mentioned, I'm an old fart. And so I use, terminal text editors because, I have never grown up, and, this is the way that I wrote programs back when I started. So I just gotta keep living that way. All right, what I'm gonna do today is I'm gonna talk, sort of give you a preview of the major aspects of Reach that are talked about in the tutorial. Then what I'm going to do is I'm going to give you a little bit of insight into some of the more advanced material that's talked about in our workshop. And then finally, I'll talk a little bit about where Reach is going in the next quarter. What I would say is that watching this video and participating is not a substitute for going through the tutorial or any other learning materials that we have on the Reach documentation site. Think of it more as like a preview to help put that material in context and maybe pique your interest a bit to want to get involved in doing it. So just to comment a little bit about how the documentation is organized, what we have is that we have the overview. And what the overview does is it walks through sort of the key ideas about what writing a Reach program is like. It talks about what a decentralized application is, how you compile Reach programs, how they get verified, how you can break them, how you can break a decentralized application up into multiple pieces and which pieces Reach handles and which ones it doesn't, and then how to build a very simple web application for a decentralized app. So that's what the overview is about. The tutorial is a step-by-step incremental way of building a particular program. In this case, it's a program that allows two people to make a wager over the outcome of a game of rock, paper, scissors that they're going to play. Now, since rock, paper, scissors is basically a game of chance, you can kind of think about it as it's a really simple two-player gambling application. But we think that the rock, paper, scissors application is good because it's a domain that everyone understands. What I mean by that is that, when you program, there's always the thing that you're making and then the tool that you're using. And if you have to understand the thing that you're using, the thing that you're making in addition to the tool, then now you have to learn two things. So for example, in the blockchain world, we talk about ideas like a DAO or an automatic market maker. And maybe you don't know what those things are, so you need to learn about that before you can even start learning about what blockchain development is like. In contrast, my little kids downstairs, who are in elementary school, they intuitively understand what rock, paper, scissors is. So that's why we choose this as an example. The next part of the documentation is what we call the guide. And basically what the guide does is it talks about the big ideas about Reach, and it tries to answer questions that one might have about how it's organized, why is it written this way. What the workshop does is it sort of continues the learning pattern of the tutorial with a series of self-study projects, where basically rather than us walking you through every line, instead we sort of start from a specification and say, how would you design this? And then we gradually reveal how we would do that design. And the intent of the Reach documentation is not to make you an expert Reach programmer, but to make you an excellent DApp developer, so you can understand what the core ideas of DApp development is. And I think the workshop is a key part of that. Finally, we have the reference, and the reference is like a exhaustive technical reference of every little part of the Reach language. So, when you look at it, you can see exactly what functions are available for interacting with arrays, for instance, and exactly how they work and what they're called. And every time when you look at Reach documentation, the variables that appear in programs, you can click on them and go to where they're documented. So for instance, like if I were to look at this program, for instance, see how it says assert right here? Well, I can click on assert and we'll go and talk about the documentation for how assert works. And so then if I'm reading assert and I can see, oh, what's a static assertion? I can go click on this and look at it. Essentially what we've done is we've made it so that the reach documentation is basically a self-contained wiki textbook style thing that describes in excruciating detail what a decentralized application is. You can definitely get down a rabbit hole as you try to learn every little aspect of it, but it's not intended for you to need to know every little detail. We just want to make sure that all those details are available if you want to look at them. All right, with all that preamble out of the way, let's get down to an actual program. So over here on the left side of my screen is a really trivial reach program. Now, when you write a reach program, you are literally writing a JavaScript program. You can kind of think of it as like, you're writing a JavaScript program that uses this weird library. And in this weird library, there's this part that's called reach app. And what reach app does is it allows you to write an application. And as Chris mentioned before, when you program a reach program, we imagine you giving like stage directions, you might say, to individual actors who are participating in some decentralized computation. So in this case, those actors are Alice and Bob. And these names right here in these strings are just giving pleasant names for those roles. And then these variables A and B, they are basically the handles inside of the program for those actors A and B. And then what is in between these lines right here, these braces, are the actual program. And in this case, the program does literally nothing. It just exits the program. So this right here is like the most minimal syntactically correct reach program. If we were to compile it, it literally would do nothing. But now this program right here, what does it correspond to in sort of the normal world of blockchain development? I'm going to turn to my video for just a moment because I want to use my hands to make motions. So normally when you write a blockchain program, you really write 3 different programs. We'll put one program right here, one program right here, and one program right here. The main thing that gets the most attention is the smart contract. The smart contract is a program that runs on the blockchain on virtual machines like Ethereum, like the EVM, or like the Teal virtual machine and things like that. Then the other thing that you do is you build a front end, and this is like a website that interacts with that program. Now, typically, your website will not directly contact the smart contract. Instead, what you'll typically do is build a middleware layer, just like we build middleware when we're writing full-stack web applications. And what that middleware does is it basically interacts with the smart contract and provides an external interface to the front end that smooths over the complexities of dealing with the blockchain protocols. As an analogy, if you're a full-stack developer, it's natural for you to make a front end that contacts your server, and then your server contacts your database. Your front end does not typically directly contact your database. That middleware provides that abstraction layer. So the same structure is very common in decentralized applications. What Reach does is when you write this one program, it simultaneously creates the smart contract and a unique middleware for each one of the participants. So in this case, we're going to generate a smart contract. We're going to generate a middleware for Alice and a middleware for Bob. And then we can take those 2 middlewares and build front ends. Now, typically, decentralized applications have a notion of peer participants, meaning that like Alice and Bob might actually have the same user interface, but they are logically separate actors. So we can actually look when we compile this program. So I'm going to go here into this directory, and I'm going to compile the program. So I'm going to run reach compile. And what it's going to do is it is going to actually build those 2 intermediate pieces. And I'm going to turn off my video again so that my encoder doesn't burn up everything. Now, what's going to happen is that we're going to generate in this build directory a bunch of files. Now, when you run this, you don't have the developer mode turned on. So you're only going to see a few of these programs. You're going to see this program right here. And what that program is the middleware components. So if I go look at it, we'll see that there's a middleware function called Alice, and then there's another middleware function called Bob right here. So there's Alice and Bob. Those are the two middleware functions that got generated. And in addition to that, we also are going to generate the smart contract, which is actually embedded inside of this file down at the bottom. So this right here is the bytecode that would be deployed on EVM. And if we were to look up, there's also going to be the Algorand source code, because on Algorand you don't like pre-compile to bytecode. You send the source code to the node. Okay, so that's what we generated. But now, what about the front end? Well, in Reach, you would write the front end yourself, and it looks like this. So here's a sort of a minimal front end. Right here, you can see on the bottom is the minimal program, and on the top is the minimal front end. This is a completely normal JavaScript program. We require our standard library. We require the middleware that we generated. And then we just set up this front end, by the way, is going to be a purely automated test system. So right here, we load the standard library. We create 2 test accounts for Alice and Bob. We have Alice deploy the contract, and we have Bob attached to the contract. And then we actually go off and we run the Alice client and we run the Bob client. Now, this program, as I said, literally does nothing. Okay, but this is just the structure. Essentially, what we're looking at is the public static void main corresponding thing for Reach, sort of like what is the minimal thing that you need to write. But now let's go a little bit further and look at an example program. One that does a little bit more. So what I've done is I've expanded this program to be a little bit closer to an implementation of rock, paper, scissors. Let's look at the things that changed. It used to be that Alice and Bob right here had empty braces in this spot that now say player. What we've done is we've specified what the middleware interface that we expect to be provided by the front end to the back end. So this says is that the front end has to provide a function that's called getHand that allows the middleware to ask the ultimate user what hand in rock, paper, scissors they want to play. And it has to provide a function that's called cOutcome, where we can send in a number, and then that is a way of the back end of the middleware exposing information to the front end. And so now Alice and Bob, both of those 2 functions are going to expect to receive an implementation of getHand and an implementation of cOutcome. Now let's look at the actual program. As I said, what we're looking at is a JavaScript program that uses kind of a strange library. How it works is that A and B, which are the handles for Alice and Bob, what they can do is they can take independent actions locally, or what they can do is they can publish information to the blockchain. So right here we see that Alice is going to take a local action where she's going to call her getHand function and then save it in the variable hand A. And then Alice is going to publish that. Now, once she publishes it, it is now sort of logically in the context of the smart contract, which might validate that the values that were received are sensible. And then it will commit to the transaction. At that point, now Bob can do something like he can compute his hand and publish it. And then we can compute the outcome of the game and commit. And then each participant now can see the outcome of the game. Now notice that this might seem a little bit weird. See, we define the variable outcome right here. And then for each participant, A and B, we call the cOutcome function, and it receives the outcome variable. What this means is that things that are defined at the consensus level, they are available to all participants because they are public information. One of the key ideas about decentralized application development is that the blockchain is a completely public register of information about the history of a protocol. I think we're most familiar with thinking about the public nature of the blockchain ledger, but when you build a decentralized application, essentially what you're doing is you're building a different public distributed computation. And here we're building a distributed computation related to playing a game of rock, paper, scissors. And in the same way that I can, trace all the transactions from a particular Bitcoin account, we could conceivably trace all the steps of this rock, paper, scissors game in the future because it would be archived on the blockchain. Now, similarly, when B publishes their hand, that hand is now available to all of the other participants in the game because this publishing event is a piece of public broadcasting. All right, now notice that this program is a svelte 26 lines. Let's look at the corresponding front-end code. So I'm going to go open up the front-end code, and we'll see that it looks extremely similar to before. We have the same preamble of loading things, but what we also do is we have this implementation of the player interface. And when we call the Alice middleware function, we pass in a player that is parameterized over Alice. And let's look at this player. There's a getHand function that chooses a hand randomly and then prints out a message and then returns it. And then there's a COutcome function that logs a message that they saw a particular outcome. This code is also only 37 lines of code. Let's go and run it while I get ready to comment a little bit about it. I'm writing reach run down here, and I'm just telling it to only run the Ethereum mode. Now, while this is running, what I want to do is go look at the code that Reach generated for this program. Whoops. Okay. I just typed in the wrong file name. Okay, so right here we can see the code that got generated. So we see that there's an Alice function that is the Alice middleware. It takes a reference to the contract and this interaction object. If we look up the code right here, this is the contract that it receives, and this is the interaction object. That interaction object is a representation of the front end that the backend Reach code can call. Let me just open up the Reach program also so we can see all of them at the same time. Now, let's look at the code and we'll see the way that the Alice participant works. So the first thing that it does is it computes variable 3. And what is variable 3? Well, we'll see in here it's a call to the getHand function. So this getHand function right here has turned into variable 3 in the output of the compiler. While I am showing you this, you as a Reach developer never need to actually look at this file. I'm just trying to demystify and impress a little bit with what Reach is doing for you. The next thing that we do is we call in the contract to send a message, and this message contains a whole bunch of information. But if we look in the guts here, we'll see that it contains v3 right there. That v3 is publishing this hand that we pre-computed. Then what's going to happen is that after doing that computation, it's going to receive another message that's going to contain v17, and v17 is going to end up being hand B. And then what's going to happen is that we're going to compute the outcome. And so that outcome computation is right here, where we compute the outcome. And then we're going to call interact COutcome v30. So our short 26-line Reach program has become, just for Alice, a 100-line middleware layer. But there's also another one for Bob that's another 100 lines. And in addition to that, we also have, from line 203 to 585, a 380-line version of this smart contract written in Teal, which is the language for Algorand. And we also have the Solidity program that got generated, which is another 53 lines that runs the that runs the smart contract for this particular program. And it's a very simple program in this case. Now, if we go down here and we look at the code running, we'll see that it ran. It says Alice played rock, Bob played scissors, Alice saw the outcome, Alice wins. And this right here ran the program on the Ethereum network. What happened is, when you run Reach Run, it starts up behind the scenes a completely fresh instance of a developer network, so you can quickly test your program. And we have the same thing set up for when you want to use Algorand. We'll put over here algo mode, and now what it's going to do is it's going to start up a fresh instance of an Algorand network. Once it creates that DevNet, it's then going to deploy our contract to it and test run it, so that we can validate that our program works correctly. So, oh, I accidentally scrolled too far. So Algorand takes considerably longer to run in a test environment, but is considerably shorter to run in real time. And that's because Algorand doesn't yet have a developer node that runs instantaneously. So we're going to leave this running for a little bit as I push forward. And so it says Alice played paper. All right. Well, this program right here is sort of a basic program that you might imagine writing, in your first few weeks of becoming a programmer, where someone says, "Oh, write a program that does rock paper scissors." But what makes a blockchain program special, or a decentralized application special, is that in addition to being a pure computation, we can also transact funds. So let's go to the next version of this program. And in this next version of the program, we're going to extend it so that Alice and Bob have slightly different interfaces. Alice is going to provide an initial wager, and Bob will have the opportunity to accept or reject that wager. Alice is going to start by publishing the hand and the wager. Then Bob is going to potentially accept the wager. And notice that Alice is going to pay the wager, and Bob is going to pay the wager too. And then what we're going to do is we're going to compute, based on who won the game, how to split up the funds. If the outcome was that Alice won, then she's going to get 2 shares of the wager. And if the outcome is that Bob won, then he's going to get 2 shares of the wager. Otherwise, they're each going to get 1 share of the wager. So let's go run this version of the program, and we'll see what happens. So we'll go down here and run it. And while we're running it, let me just open up the front end that we modified. So in the front end, I add a little bit more code to print out what the balance was at the beginning and end. And I also implemented the wager, which is going to be 5 ETH, which is, that's very dear. This is a very expensive game of rock, paper, scissors. And then accept wager, which is just going to print out that Bob accepts it. So when we run this program, it says Alice played paper, Bob accepts the wager of 5, Bob played scissors, Alice saw the outcome that Bob wins, Bob saw the outcome Bob wins, Alice went from 10 to about 5, and Bob went from 10 to about 15. So right here, our program is not really any more complicated than it was before. The main thing that we did is we added this pay wager and pay wager in these transfer events. But if we were to go look at the Ethereum code that got generated for this, it is considerably more complicated. Let me just go open it up. So we'll open up the Solidity code for tutorial 3. And now what was once a 57-line program is now 70 lines, and it has a lot more exciting gobbledygook. So for instance, if we look down here, we'll see that there's a transfer statement where we're sending some money to the sender and some money to variable 4, and what we're sending is a certain amount corresponding to the safe multiplication of this particular value, and so on. The details of this are not especially important. It's just a computation that reflects exactly the same logic down here. Now, one of the things that you always need to be concerned about when you're writing a blockchain program is you should be worried about making mistakes dealing with these funds. So a really classic problem is accidentally making it so that your program leaves money inside of the account for the contract that is completely inaccessible to users. I imagine that you have heard of some of these stories where someone makes a mistake in their contract and now, tens of millions of dollars are locked away forever. I believe that there was a pretty high profile instance of this happening over the summer. So what does that correspond to in a program like this? That would correspond to an error where if we did something like, let's say that we accidentally made it so that when Bob won, he only got back his own share. He didn't get back Alice's share. So what I did is I changed this 2 right here into a 1. By changing that 2 into a 1, I've now made it so that when Bob wins, this program will leave money in the account. Now, here's the question. How can I detect this problem? Think about how you would detect this problem if you were writing a traditional application. What you might do is you might try to get what people call code coverage, where you might try to implement a whole bunch of different tests to make sure that this line of code were reached. And then what you would do is you would have to manually implement inside of your test environment this check to make sure that there was no money left over. Okay, that of course relies on you being a great programmer, realizing that this is a problem, and actually being able to synthesize all of those test scenarios and actively check them. Let's see how Reach allows us to catch this problem. I'm going to go back and I'm going to try to run the program, which is going to cause it to get recompiled because the file is updated. Now when I run it, it says, oh, I was checking 16 theorems and 4 of them failed. And actually look right here. It says that on line 42 of your program, which 42 is the last line of the program, there was a balance assertion. That balance assertion said that was formalized as this. It said 0 has to equal this amount right here. Now, what is that amount? That amount is how much money went in when Alice put in the wager, how much Bob put in when he put in the wager, how much money went out to Alice, and how much money went out to Bob. So this right here is the value of the balance at the end of the program, and it's saying that had better be 0. Now notice that what we have seen is we've seen this program as a little JavaScript program. So it says that this assertion had better be true. And it says that there is a violation witness. Now what a violation witness means is this is a concrete example of a way to run this program where you would find an error. What Reach has done is it has discovered the test scenario that you would have hopefully written yourself that would have found this problem. It says, well, if you had run it so that the wager was 5 and v3 was 0, which is the result of calling Alice's get hand, and Bob's get hand was 4, so it's saying if this was a particular way to play the game, then in that case, v32 would have been a 0, and we can recognize this as that's the computation that figures out who the winner is. And then v39, that's the part of our program that is 4a and 4b. And then that would have been 0 and 1, which is this line right here. And then that means that this expression right here would have been false. And so what it has done, it has figured out for us a concrete way to run the program that would reach an error, and has shown us what would go wrong exactly, in particular that the balance at the end would not equal 0. Notice that it did this instantaneously. So I didn't have to, go pay someone $100,000 and wait 6 months to maybe get back an answer. It happens as fast as I can type. The only reason that it's slow is just because it's buffering to the screen because I'm recording. So it does this instantaneously, and it would do it no matter what we did here. Now you might think like, oh, what if I tried to do something more complicated? Like, is there some way to like trick this? What if I did like 5 plus 10 minus 9? Is that gonna cause a problem? No, it's not going to cause a problem. It's going to detect the same situation. Although actually in this case, it's going to have a different problem. It's going to say that this right here, by the way, 5 plus 10 minus 9 is 6, but there are only 2 shares. So this actually is a different assertion that's on line 37 right here, right there. And it says that it should have been the case that the amount that we're transferring to Bob is less than the amount that's left over in the account, but that's not true. Because if the wager were 1 and v3 were 2 and v17 were 0, then that means that the outcome would be 0, and then you'd be trying to give Bob 6 shares, and that's not possible. So notice that it detects all sorts of different violations that we could have without us having to go through any deep effort of trying to verify our program. We don't even think about it as that we are verifying our program. Instead, what Reach does is it automatically verifies it. And of course, now I've changed it to be correct, and it passes. The way, of course, that it does this is, as Chris mentioned, it takes your program and it turns it into a system of equations such that if that system of equations has a solution, then your program has a violation of one of its theorems, and we can look at the violation and give you back that error message that says you could have run your program in this way and there would be a problem. Okay, well now let's push forward a little bit and make this program a little bit better. Now, something that's interesting about this program is that notice that Alice publishes her hand in the clear. That means that Bob actually, he could look at her hand before deciding what he was going to do. So we could actually write a program where what Bob does is he just looks at Alice's hand and just pre-computes what would allow him to win. And then what he can do is we can just assert that he's always going to win. Now that's unfortunate because it means that this program is fundamentally broken because Alice publishes this information in the clear. And Reach actually helps us formalize this. Well, it also helps us protect against this. Because what we can do is we can modify this program to use what's called the commitment pattern. A commitment pattern is a really standard thing in cryptography, where rather than sending someone information in the clear, what I do is I send someone a secret hash of that information. What this does is it pre-commits me to using a particular value later on in the program. So what I do is I commit early on to a particular hand, or at least Alice does. And then she publishes that commitment. Now, what Bob can do is we can use Reach to write down the theorem that Bob cannot know Alice's hand or Alice's salt. And when we run this program, it's going to say that it's proved more theorems. Those more theorems that it proved included this one. Let me just go to that real fast so we can see while I'm talking about it. So it used to say that it proved, I think, 16 theorems. But now, whoops, let me just clean. But now it's going to say that it's going to prove 41 theorems. So it's proving more stuff. And one of the things that it's proving is this theorem right here that says that B cannot know A's hand or salt. Now what B does is B has to publish their hand in the clear, but that's also safe because Alice has previously committed to a particular hand, which he then publishes. We then check that it's accurate, and then we compute the winner and go on as before. So what this does is it now has guaranteed that our program doesn't suffer from this vulnerability. Every time you write a program that has an error, you should ask the question, how can I get my programming language to prevent me from writing such an error in the future? And in this case, the problem with the person's program is not that they didn't know about the make commitment function, it's that they failed to write down the theorem that B should not know something. And if they would have written down that theorem, it would have been violated, and that would have led them to discover the commitment pattern. And this is one of the tools that Reach provides to users. It provides a path from programs with errors, programs that are wrong, to programs that have compile time errors, into programs that are correct. That is the ultimate path that we want to do. We would like it so that every erroneous program is also a program that our compiler can detect an error with. Well, let's look at the next thing that we provide in Reach, which is that our verification engine is not just used for detecting problems with how you transact funds or how you deal with knowledge. Instead, what it can do is it can be used to write down essentially a test environment, test cases for your program. So what I have right here is I've abstracted away this winner function a little bit, where we have winner, hand A, hand B, and it has that computation. And I've named the values 0, 1, 2, and 0, 1, 2. And what I've done is I've written test cases embedded in the program, where I've written the assertion that the winner of rock and papers is B wins, the winner of paper and rock is A wins, the winner of rock and rock is draw. I've also written the theorem that whenever you send in any hands, the outcome, the output of the winner function is always a valid outcome. I've also written the theorem statement right here that for all hands, whenever that hand plays itself, you get a draw. Now, when I run this program, as we saw, it said that there were 41 theorems that it proved, and that includes all of these right here. Those are all things that it verified. Now, what I could do is let's just see what happens if I accidentally make a mistake. Let's accidentally, quote, accidentally put in an error. We'll say, well, if hand A is rock, then in that case, this is going to be like a secret way that A will just always win. If it plays rock, it'll just always win. Now, when we run this program, it's going to say that there are violations of the theorem. So see that it said there are 41 theorems and 4 of them failed. It said that if you look, that on line 10, this theorem was formalized as false. So if we look at line 10, it's this one, because it turns out that we can statically compute that this is false, and we know that that's just wrong. So you thought that this was true, but it's actually false. And if we, okay, let me fix that. Okay, there we go. Okay, let's look at the next thing that we can do. So the next thing that Reach does is it allows you to make it so that your program is safe against non-participation. I'm only going to briefly explain this, but basically, whenever you write a blockchain program, you have to deal with the possibility that someone will just walk away and never come back to the computation. Because, of course, there's nothing forcing them to do that. And so if that were the case in this particular program, imagine that A paid in to the contract, but then B decided to never accept the wager. Well, in that case, A's money would just be locked away forever. So what we can do is we can specify that after a given amount of time, then A is going to come back to the program and extract all of the money out. Similarly, if A refuses to publish their hand after they've observed Bob's and they know that they're going to lose, we can make it so that Bob can come and extract all the money. So this again is another common pattern that shows up in blockchain programs where you are essentially penalized for ignoring the program and not continuing to participate, and that's a feature that is directly built into Reach. Finally, what if we wanted to modify this program so that we continued playing until we reached an outcome that wasn't a draw? So what we can do is we can insert a while loop in our program that says, while the outcome is a draw, play a round of the game and compute a new outcome. And so what this is going to do is it's going to keep running until the outcome is either A wins or B wins. And at this point, we've written a fairly fleshed out game that's only 88 lines of code. And if we were to look at the front end for it, it's also only 60 lines of code. So we got 140 lines of code total. But now, what's the damage on if we were to have written this in pure Solidity? Or what if we were to write it with the backend tool ourselves? So our middleware and the Algorand contract, actually, let me write it like this. Okay, so our Algorand program is going to be 1,600 lines. Our middleware is going to be this number minus that number, so about 2,000 lines of code. And our Solidity program is going to be about 450 lines. So this is what you would be expected to write yourself if you were using a tool that wasn't like Reach, that didn't have this high-level perspective. And of course, all of this code you would then have to verify was actually correct, which of course is done automatically by Reach. Now, one question that we often get at this point is, this is very interesting and it provides this, high-level way of programming applications like this, but does this scale for the sorts of things that people do today actually on the blockchain? So I want to show you 2 examples. So remember, our rock, paper, scissors program is 88 lines. So what I want to do is go look at something called the FOMO program. So if you were around in blockchain in 2018, you may remember this program that was called FOMO 3D. Basically, FOMO 3D is a lottery where whoever buys the, quote, last ticket. Now, what is the last ticket? What I mean is that imagine that people are coming into a convenience store buying tickets to this lottery. And if it is ever the case that it goes 24 hours without someone buying a ticket, then no more tickets are sold, and the last person to buy a ticket, they win the pot. So this was actually launched on Ethereum back in 2018, and the contract at the time had, I believe, $5 million worth of ETH in it. Of course, that would be, like 50 million or something like that, or some absurd number today. But back then it was 5 million ETH. So this was an extremely popular game that people played. And ultimately someone won it. They won it through a very exciting way, which I won't elaborate on, but this is a real thing. Okay, now let's look at writing that program in Reach. Now this program, compiles, runs, there's a test environment and all that stuff. So first of all, I just want to pop to the end. This program is 68 lines of code. So it's actually simpler than rock, paper, scissors. And we can see its simplicity in the following way. It has two kinds of participants. The funder of the program, of the game. That's the person who starts it. And then a buyer of a ticket. Now the funder interface is that they set the parameters of the game. They set the ticket price and they set the deadline. That's the 24 hours. And then everyone shares the show outcome function. And then a buyer, there is actually an entire category of them, which we call a participant class. So with the game of rock, paper, and scissors, there's only one Alice and only one Bob who play against each other. But in a decentralized application like this, there are many people buying buyers, and so we call that a participant class. Now they have a function that decides whether or not they should buy a ticket, and they see they get to see every other person that bought one. Okay, so the first thing that we do is that the funder computes the ticket price and the deadline and publishes them. And then what we do is we use a fairly advanced feature of Reach that's called parallel reduce. What parallel reduce does is it computes a set of variables. So in this case, the variables keep going, winner, and tickets sold. And they are initially set to true, the funder, and 0. And then what happens is that this block of code continues running until either the while condition is false or we reach a timeout. And how it works is that each case, in this case there's only one, gets to have a chance at running. So you can kind of think of a parallel reduce as being like a race where a whole bunch of people compete to be the one to run this part of the program. And if they succeed, then they get to run it. And if they fail, they don't. And afterwards, they could try again. And they could keep trying until either this condition is false or the timeout happens. Okay, now what is the condition? Sorry, what are the cases? Well, the buyer decides if they should buy a ticket. They pay in the ticket price. And then what they do is they set themselves, that's this, to be the winner, and they increment the number of tickets sold to be more than one. And if instead there's a deadline, the winner stays the same, the ticket price stays the same, or the ticket count stays the same, but now keep going is false. And now when we're done, whoever bought the last ticket, they receive everything, and then the game is over. So this program is exactly the FOMO 3D program. And we can look at the code that gets generated if we want. And we can see that this Solidity program is, 279 lines, and you could walk through it and try to understand what it's doing. It's fairly straightforward, but you don't need to worry about this. You can instead focus on the high-level program that specifies the whole big idea. Now, what if we wanted to make a generalization of the FOMO program where rather than only the last ticket winning, what if we split the proceeds evenly between the last 5 winners, let's say? How much more complicated do you think that program would be? Well, let's look at it, actually, because we did that. So what we did is we made it so that there's a global variable that's called the number of winners. And so in this case, it's 3. And now what we did is we've just generalized each piece. So rather than there being a single winner, there's now a number of winners. And the main thing is that we now have an array of winners, which starts off as just the funder. The funder is sort of being presented as all of the previous winners. And then what we do is we make it so that whenever you sell someone, you take a particular spot in the winners array, and then you keep going. And then what happens is each winner receives a particular reward, and then whatever the remainder is goes to the funder if if the total balance doesn't match the number of winners. Now this program is now it's also 68 lines of code. So it's actually the same length. It's just that we reorganize things to make it a little bit more concise. And so by making it a little bit more concise, it's the same amount of code. Now, what about the Solidity code? Is it the same number of lines? Whoops. Whoops. Okay. Workshop, FOMO generalized. Oh, and actually I haven't built this, so I gotta go build it. That's why it didn't load. Okay, so no, it's considerably longer. It's, you know, like what is it? It's like 80 lines longer to have more logic about dealing with the 3. Now, the other thing, though, is that this Solidity program, if I wanted to change it so that rather than there being 3 winners, let's say that there were instead 30 winners, well, with the Reach program, I just changed the 30 right there, and now I just compile and it all just works fine. It turns out, however, that it's not as simple as just changing some for loop somewhere in the Solidity program to make it 30, because of the way that Solidity works at that state machine level that we talked about before. Because we're programming at a higher level of abstraction, we can make more cross-cutting changes to the program more easily. Let's look at another program that's kind of in the same category of a big program that people are familiar with. And now here, I'm going to actually show you a program that doesn't actually work yet. It is kind of the target for the next thing that we're working on. And so here is a version of Uniswap that relies on a few features that I haven't yet implemented in Reach. So I just want to sort of give you a preview. So this program is fairly long, you know, it's 270 lines of code, but in contrast, the normal implementation of Uniswap is about 3,000 lines of code. And this one is fully formally verified, and it includes that middleware layer, and it includes the smart contract itself. Now, the way that this program works is it's considerably more complicated because, you know, we have an admin participant, we have a provider, and we have the traders. And then we also have a number of tokens that they interact with, and a token that is minted and controlled by this particular contract, or this particular program. Now, what I have up here on the top of this program are just basically math logic working out how to update the market parameters that are used in Uniswap. So, but I'm going to instead focus on the actual Reach program, where the administrator publishes the parameters of the fund. And then what happens is that the administrator is allowed to close the fund anytime they want. Providers can withdraw liquidity. So this is, you know, just one piece of logic, you know, that's for this one thing. Now notice this program is, the majority of this program is comments, explaining how it works and annotating what pieces of Reach will be needed. Providers can also deposit funds. Traders can perform swaps. And so these are the fundamental pieces of what this program does. It is still, we're still able to program it at this participant level without thinking about the state machine level. And we can write in a high-level JavaScript language that compiles down to a large amount of Solidity that implements the same ideas, but of course, in a much lower level way. So this kind of concludes what I wanted to talk about. Now, I do want to say, like, well, if you're going to do this, if you're going to walk through our tutorial, what are you going to see? If you go through our tutorial, these first steps are going to walk through that rock, paper, scissors program from front to back. Afterwards, you could then go and look at the workshop, and the workshop has in it as steps 4 and 5, that fear of missing out thing. And then if you go even further, then you can learn more things, and we'll eventually write a workshop about how things like Uniswap and whatnot can be constructed. I was, of course, happy to take questions before, but now is the real great time to ask questions because I don't really have anything else that I want specifically to go over right now with you all.
Thank you, Jay. And if you feel like you were drinking out of a fire hose, that's okay. Jay went over about the entire tutorial, which the tutorial should take probably 4 hours, and he did it in 40 minutes. So, so don't worry if there's a lot of information.
Yeah, the other thing that the tutorial talks about, just kind of as an FYI, is how you can write your front end as a web application. Because as I mentioned, the JavaScript that we generate, the JavaScript that you can write as a front end is completely normal JavaScript that doesn't use any weird things about Reach. Reach is just some library. So that means that all existing JavaScript code that you're familiar with and all the existing JavaScript tools that are popular, you can just use those in that front end. So for instance, we have in the tutorial, we walk through how to develop a React-driven web interface for the rock, paper, scissors program. And we walk through every little part of it as well. I didn't go through that because I don't know what a website is. I've never used one before. I just use text editors.
And one thing to kind of highlight as well is that, as Jay said, you write this application once and it compiles for both Ethereum and Algorand. But why would you care about that? One of the things, kind of shill Algorand a little bit is the cost of transactions and the transactions per second that I can handle are 1000x better than what Ethereum is. I mean, I believe a single transaction is 1/1000th of a penny, and Algorand can handle over 1000 transactions per second right now. And you don't need to learn a completely different technology to be able to launch on it. So it allows you to actually write to the application and launch it on the protocol that best fits your needs. Because, for example, right now with rock, paper, scissors, I probably wouldn't play rock, paper, scissors for less than 5 ETH that Jay did on the actual main network, just because it costs multiple dollars to do a transaction. But I would probably play against rock, paper, scissors on an Algorand for whatever price, because I can afford 1000th of a penny.
Yeah. So I mean, like, if you and I wanted to bet $5 on rock, paper, scissors, we could do that with Algorand, and the gas prices would be negligible. In contrast, if you and I tried to bet $5 of ETH, we would pay $150 in gas prices.
Hey Jay, I don't have an immediate question about. Thank you for the presentation. It was really great, and I definitely see the value add and how much it saves time for developers. So I'm excited to play around in Reach. But I kind of want to spend time like after this is done, like going through the tutorial myself at a much longer rate or amount of time. But if we have questions, is there a way we can like connect with you if we're working on just like fun projects, or if we get confused in the tutorial?
Yeah, totally. So on the documentation, there's a link right here that says start a discussion on the Discord community.
Nice.
You can go to the Discord and it'll invite you in, and right now there are 65 people online. We got 510 members right now. It pings on my phone and my kids are always like, Dad, why'd you stop reading? I'm like, oh, I'm answering a question that someone has on Discord. So yeah, so we're constantly interested in helping people.
Okay, great, thanks.
That's actually a great segue into like where is Reach right now? How many users do we have? How is this something that is going to stick around? And the answer is, our mission is to monopolize all blockchain developments. Like, we will be the way that the majority of people in the world are writing their blockchain applications. And that sounds like a pie in the sky type of idea, but since we launched in September of last year, we have actually grown by 10 to 20% every single week since we've actually launched. So, and not only that, but we're averaging more developers on the Reach platform than many of the protocols themselves. So we already have a point where if you have a question, there's many people in the community that will be glad to help you. And now's the time to be part of the early crew, maybe get a sticker. We just changed our logo, maybe get a t-shirt, who knows?
Yeah. Do you want to talk about the prize that we're working on, or are the details of that not worked out enough?
um, you know, why not? We're all friends here, right? So one of the things that we're actually working on right now is we're working with a pair of VCs, venture capitalists, to create a new grant fund that we'll be able to give out money to our community members that have ideas on what they want to build. This is not solidified yet, but we are actively talking to people in our community, people that we know that have ideas, to be the first ones to receive the grant money. And this is not we're not taking equity. We really want to see you be able to have the ability to focus on building your application and building amazing things. So if you do have an idea, or maybe if you don't have an idea and you have interest in building, we have ideas. So come on over, talk to me, reach out to Jay and I, and we'll be happy to start those conversations so that you can be full-time blockchain developers. Doesn't that sound like fun?
Christopher, what's the best way for people to connect with you? Is it through Discord or?
Sure. There's Discord's great. Come join our community. I talk a lot, so I'm pretty approachable, I would think.
Awesome.
And the other thing too is that don't want to shell this too much because, like I said, we're still in the process of setting it all up. But this is not just for projects as well. If you have a great way or great idea on how to create education for other developers on a way to actually create videos or maybe like a Udemy course or anything of that sort, we will fund that as well. So yeah, come talk to me. Let's get crazy.
Cool.
Well, I'm going to
sure.
stop. Oh, yeah, what's your question?
I'm sure I'm going to have questions later, but right now I'm just totally like deer in the headlights. Like I feel like I just got abducted by aliens and I saw some new technology